Right now, you're hurtling through space at a speed so fast it's hard to even grasp, over 560,000 miles per hour. Imagine that for a second. As you sit here, perfectly still in your chair, you're actually zooming through the cosmos at a velocity that dwarfs anything humanity has ever experienced. You're traveling on a cosmic merry-go-round, so vast and so ancient that light itself takes over 100,000 years just to cross from one edge to the other. This isn't just a ride around the block, it's a journey across the entire Milky Way galaxy, a home to over 400 billion stars, yet none of us have ever seen it from the outside. We don't have the luxury of stepping back to witness its true scale. But what if we could? Tonight we're going to take you on a journey, one that will challenge everything you think you know about size, distance, and your place in this vast, endless universe. From the moment humans first ventured into space, we've been trying to understand the true scope of our existence. Astronauts talk about their first moments in orbit, staring down at Earth from above. At 250 miles up, the familiar landscapes of cities and mountains become tiny smudges, barely visible from that distance. But what might be even more mind-blowing? Not even your own home can be seen. From space, you lose sight of everything that once felt so big. It's like standing on the edge of an endless ocean, where everything you know seems impossibly small. And then we pull back even further, looking beyond our planet, beyond our solar system, beyond the Milky Way. As we zoom out, the space around us only grows more vast, more isolated, and we begin to realize just how tiny our home really is in the grand scale of the cosmos. This isn't science fiction. This is the true, staggering scale of our universe. And what comes next might just change how you think about our place in it. So buckle up. This cosmic journey is just beginning. Imagine you're an astronaut. You're sitting aboard the International Space Station, peering out of the small window that gives you a glimpse of Earth below. At first, everything is normal. The swirling clouds, the oceans, the mountain ranges, the sprawling cities. It all looks so familiar. But then, you start to notice something unsettling. As you look closer, the details begin to fade. Cities that once seemed so massive from the ground are now reduced to tiny patches of light. The vast mountain ranges you once crossed in a car, the places you thought you knew like the back of your hand, now seem no bigger than the creases in a piece of crumpled paper. And then, it hits you. You can't see your house. In fact, you can't see any house. You can't see a single person, not even the place where you grew up. From 250 miles above the surface, all those things that once felt so close and personal are completely invisible. The individual buildings, the streets, the parks, they've all vanished, completely lost in the vast expanse of the planet below. This moment is one of profound realization for astronauts. It's a reminder of something that we rarely stop to think about. Scale. The scale of Earth, and more importantly, the scale of everything in our universe, is far more mind-boggling than we typically grasp. We live our lives on the surface of a planet that feels to us infinite. We think in terms of miles, hours, and cities. But when viewed from space, our planet becomes just a small speck, so small, in fact, that even the most monumental landmarks disappear. From this perspective, we are nothing but tiny, fleeting creatures on an insignificant rock floating in a vast emptiness. Now, let's stretch that perspective even further. What if we didn't stop at 250 miles? What if we pulled back even more? 1,000 miles, 10,000 miles, 100,000 miles, 100,000 miles, 100,000 miles. The view would be nothing short of staggering. From a distance of just 10,000 miles, continents would begin to blur together. The Earth, which once felt infinite when you stood on its surface, would now shrink into a pale blue dot. And that sense of infinity that humans have always felt, that innate connection to the planet beneath us, would begin to unravel. The idea that the Earth was all there was, that it was the center of our universe, would become harder to hold on to. As we zoom out even further, it's as if we're on the brink of stepping off the edge of what we can comprehend. At 50,000 miles, Earth is just a distant dot floating in the vast emptiness of space. But even more astounding is the space around it. The blackness of the void that surrounds us stretches out in every direction, empty, endless, almost overwhelmingly quiet. But here's the thing, even in this blackness, Earth is not alone. It is part of something so much bigger, so much more intricate, that it can be hard to even begin to understand. We are not just floating in isolation. We are on a ride, one that we don't fully understand, through something that is far grander than we could have ever imagined. Our planet orbits the Sun at a speed of about 67,000 miles per hour, and it's doing this while spinning on its axis at 1,000 miles per hour at the equator. That's fast, really fast, but even that speed is nothing compared to the velocity of the solar system itself. Our entire solar system, all the planets and their moons, is hurtling through space at a jaw-dropping 560,000 miles per hour, carried along by the gravity of the Milky Way galaxy. As we sit here, perfectly still in our chairs, we're actually moving through space faster than any human has ever moved, and yet we can't feel it. The sense of motion is so grand, so unfathomable, that it's nearly impossible to comprehend from the surface of Earth. It's as if we're living inside a giant, swirling cosmic whirlpool moving through the universe at unimaginable speeds, and we're completely unaware of it. But why are we moving at all? Why is everything hurtling through space in the first place? To answer that, we need to step back even further. The Sun, along with its family of planets, moons and comets, orbits the center of the Milky Way galaxy. This center is located about 26,000 light-years away from us. That's an unfathomable distance, a number so large that it's hard to make sense of it. The center of the Milky Way is a place of extreme gravitational force, and our entire solar system is bound to it, like a stone whirling at the end of a string. And just like the stone, our orbit takes us around the center of the galaxy, on a journey that spans an incredible 200, yes, you read that correctly, 250 million years to make one complete orbit. To put that into perspective, our solar system has only completed 18 full orbits of the galaxy since the Earth formed. 8. This means that, in all of human history, from the first stone tools to the great space missions we've embarked on, we've experienced less than 1% of a single galactic orbit. Less than every single moment of human existence, from the rise and fall of civilizations to the discoveries of science and technology, has taken place in a fraction of a single rotation of our galaxy. And yet, we're here, living on this little speck of dust, our lives playing out against the backdrop of an incomprehensibly vast, ever-moving galaxy. But here's the kicker. Despite all of this, we still don't really know where we are in the galaxy. It wasn't until relatively recently, in the early 20th century, that astronomer Harlow Shapley discovered our solar system's true position in the Milky Way. Up until that point, we thought Earth was at or near the center of the galaxy. After all, we were used to the idea of being at the center of everything. After all, we thought the Earth was the center of the universe for centuries. But when Shapley mapped the positions of globular clusters, dense balls of ancient stars that orbit the galaxy's center, he realized that our solar system was nowhere near the middle. In fact, we were situated on the outer edge, about 26,000 light-years from the center of the Milky Way, in a region far removed from the chaotic, radiation-filled heart of the galaxy. This revelation was both humbling and reassuring. It confirmed that we were not, in fact, the center of the universe. But it also highlighted something else: how small and insignificant our place in the cosmos really is. We inhabit what could be called the suburbs of the galaxy, far removed from the violent chaos of the galactic core. Our position, though distant from the action, is actually beneficial for life as we know it. The center of the galaxy is filled with intense radiation, supernova explosions, and other cosmic forces that would make it impossible for life to survive. But out here on the outskirts, in the relative calm of the galaxy's spiral arms, complex chemistry can unfold, and life as we know it can thrive. This is where Earth, and all of human history, has unfolded. We are part of a much larger and much older story, one that stretches back billions of years and will continue to unfold for billions more. And as we step back and begin to understand the true scale of the universe, we can start to see just how small we really are, how fleeting and fragile our existence is in the grand cosmic theatre. It's a humbling thought, but also one that can spark a sense of wonder and awe. Because when you really think about it, we're not just living in the Milky Way, we're living inside one of the most mind-boggling, awe-inspiring structures in the entire universe. When we think about the vastness of the universe, it's easy to get lost in the numbers. We hear about light-years, distances too enormous to wrap our heads around, or the number of stars in a galaxy, and it all starts to sound like abstract math rather than something real. But what if we could actually feel the enormity of the cosmos? What if we could understand it in a way that isn't just numbers and distant, unreachable facts, but something we can actually picture in our minds? Let's start by thinking about just how far we've come. The idea of space used to be something abstract and terrifying, something out of human reach, a place where the Earth ends and nothing begins. For centuries, people thought the stars were just tiny dots stuck to a giant dome above us, part of a vast sky that held no real meaning. The idea that we could leave the Earth, that we could venture out into this endless void, was once considered a wild fantasy. And then, suddenly we were there. We left Earth and we went to the moon, and it changed everything. For the first time, we saw our planet from above, a beautiful, fragile ball floating in the vast emptiness of space. It was something no human had ever seen before. From that moment, everything changed. We began to understand our place in the universe, not as the center of everything, but as part of something so much bigger than we could have ever imagined. Our perception of Earth shifted in an instant. The world didn't feel like the center of the universe anymore. Instead, it felt small, isolated, and precious. That shift in perspective didn't stop with the moon. Over the years, as we've sent more astronauts into space and launched increasingly sophisticated probes into the cosmos, we've gathered more and more information about just how big and how far-reaching the universe is. And the deeper we look, the more awe-inspiring it becomes. The more we understand, the more it seems like our tiny blue planet is just one insignificant dot in an unending stretch of space and time. So let's take a step back and consider just how vast our cosmic neighborhood truly is. We call it the Milky Way, but the name doesn't even begin to hint at the scale of what we're talking about. It's not just a collection of stars. It's a vast, swirling spiral of stars, planets, gas, dust, and dark matter, all bound together by the force of gravity. And when you stand on Earth and look up at the night sky, it's easy to forget how small we really are in the grand scheme of things. The stars we see are distant suns, each one a giant nuclear furnace burning billions of times brighter than our own sun. Yet they look tiny, almost like flickering fireflies in the sky. The truth is, those stars are far, far away, so far away that it's impossible to truly fathom the distance. Take Proxima Centauri, for example. It's the closest star to our own sun, but it's not exactly close in the way we think of proximity. In fact, it's over 4.24 light-years away. That means that the light from Proxima Centauri takes over 4 years to reach us. And that's just the closest star. When we start talking about the rest of the galaxy, the distances get even more mind-boggling. Our Milky Way galaxy alone is roughly 100,000 light-years across. To give that some perspective, if you could somehow travel at the speed of light, which for now is impossible, it would still take you 100,000 years to cross the Milky Way from one side to the other. That's not a journey you could make in a single human lifetime or even over generations of lifetimes. And yet, the Milky Way is just one of billions, if not trillions, of galaxies in the universe. Some are smaller, others much larger, but all of them contain countless stars, planets, and other cosmic phenomena. To put it simply, we're living in a universe that's beyond our comprehension. It's easy to look at the stars and think that what we see is the full extent of what's out there. But that's just a tiny fraction of what exists. The Milky Way itself contains somewhere between 100 and 400 billion stars, each with its own set of planets and moons, maybe even its own form of life. But even that mind-blowing number is just a drop in the ocean of the universe. When we look at the vastness of space and the number of galaxies that exist, we begin to realize that we are not just insignificant in terms of the size of our galaxy, but we're also part of something far, far larger than we could ever imagine. But it doesn't stop there. Even beyond the stars and galaxies, there's something else at play, the dark matter that makes up most of the universe. While we can't see dark matter directly, we know it exists because of its gravitational effects on galaxies and stars. In fact, dark matter is thought to account for about 85% of the mass of the universe. So while we can see stars and galaxies, we know that there's far more out there, hidden from our view, shaping the cosmos in ways we're only just beginning to understand. In addition to dark matter, there's another mysterious force out there that shapes the universe: dark energy. Dark energy is thought to be responsible for the accelerated expansion of the universe, pushing galaxies apart at increasing speeds. But again, despite its powerful influence, dark energy remains something of an enigma. We know it's there, but we can't see it, touch it, or interact with it in any way. It's just one more piece of the puzzle that we don't fully understand. Now, if all of this sounds overwhelming, it's because it should. The universe is so vast, so mysterious, and so complex that it's difficult for our human brains to truly grasp its scale. But that's what makes it so fascinating. Every time we make a new discovery, whether it's finding a new planet or detecting the faintest signs of dark energy, it opens up a new chapter in our understanding of the universe. We're constantly learning, constantly expanding our knowledge, and constantly amazed by how much we don't know. But even as we try to comprehend these vast distances and forces, there's one thing that remains constant. We are part of this universe. We are not detached observers. We are here, on this tiny blue planet spinning through space at incredible speeds, surrounded by a universe so large and mysterious that it seems almost impossible to believe it's real. And yet it is. We are living in the middle of one of the most incredible, mind-boggling, awe-inspiring things in existence. So the next time you look up at the night sky, take a moment to consider the vastness of the universe. Think about how far away those stars really are. How many of them have planets of their own? How many galaxies exist beyond the Milky Way? And then maybe, just maybe, you'll get a small taste of the true scale of the cosmos. Because what we see when we look at the stars is only the beginning. The true wonder, the real mystery, lies in everything that exists beyond our view, beyond our understanding, and beyond our imagination. And as we continue our journey through the universe, there's no telling just how far we'll go or what we'll discover next. Imagine for a moment you're in the cockpit of a spacecraft, floating in the cold, silent vacuum of space. As your eyes take in the vast, sprawling landscape of our planet below, it feels surreal. From this vantage point, the Earth that once felt like the center of everything, the place where you've always lived, loved, and learned, is now a distant, fragile orb. The blues and greens of the oceans, the whites of the clouds, and the browns and greens of the land masses seem to merge into one, an almost ethereal blend of colors. The mountains and valleys which once stretched for hours and felt so enormous, now look like tiny wrinkles on a sheet of paper. As your gaze shifts, you start looking for landmarks. Maybe your city, your house, even the street you grew up on. But no matter how hard you try, you can't pick out a single recognizable detail. From just 250 miles above the Earth, the resolution of human vision simply can't capture something as small as a house, let alone a person or a car. It's as if all those things that defined your world, that once felt so important, have been erased. The cities you once thought were massive, the places where entire civilizations have thrived, have shrunk to tiny specks of light scattered across the surface of the planet. At that moment, something profound happens. You begin to realize that distance, in its most literal sense, erases detail. What once seemed so massive and important, something you could touch and feel, is now completely invisible. From space, cities disappear, neighborhoods fade into indistinct patches, and even entire countries become smudges of brown and green. What felt like an unending expanse when you were on the ground now seems minuscule from this high up. The vastness of the Earth, the expanse of the continents, becomes almost laughable from this perspective. It's humbling, even startling, to realize that everything you once knew, everything you once thought was important, is now just a tiny speck in the overwhelming scale of the universe. But what's even more startling is the realization that this feeling of smallness doesn't end with Earth. No, it only grows as we take a few more steps back. If you could somehow zoom out from the Earth, say by 1,000 miles, the view would begin to change radically. At a distance of 1,000 miles, the entire continent of North America would start to fade, its borders barely visible, blending into the surrounding oceans. The scale of Earth itself would continue to shrink, until all you would see is a faint blue dot, floating in the infinite blackness of space. And then, as you continue to zoom out, this dot would get even smaller. At 10,000 miles, Earth becomes no more than a pale blue marble, floating in the vast emptiness, and the black void surrounding it would stretch further and further. The distances between objects, between stars and planets, would start to feel like an insurmountable gulf. Imagine that. If Earth were the size of a marble sitting on your desk in front of you, the nearest star, Proxima Centauri, would still be more than 4,000 miles away. Think about that for a second. A marble just sitting on your desk, and the nearest star, the closest thing to us in the entire universe beyond our own sun, would still be farther away than the distance from New York to Los Angeles. Even that distant star, the one closest to our own, would seem an impossible distance away, like trying to throw a stone to the farthest shore with no hope of ever reaching it. And what's even more mind-boggling is that the space around us, the emptiness between objects, is far larger than we can even begin to comprehend. To drive across the United States, for example, it would take you about 5, but if you were to travel at the speed of light, which in human terms is a mind-boggling 670 million miles per hour, it would still take you over 4 years just to reach Proxima Centauri, the nearest star outside our solar system. That's how vast the universe is. Even light, the fastest thing in the universe, takes years to travel just a few light years, a distance that seems impossible for us to grasp. But here's where things get even more perplexing. The space between Earth and the stars, between us and the vast majority of other objects in the universe, is far more than just empty space. We live within a cosmic neighborhood. Yes, but this neighborhood is not filled with the easy comforts of a home or a neighborhood park. Instead, it's filled with an unthinkable vastness, an emptiness so crushing that we can barely even conceptualize it. Between stars, between galaxies, there are voids so large that no matter how fast you go, no matter how hard you try, the space in between will always remain far too wide. If you could somehow shrink the Earth down to the size of a marble, as we've already discussed, even the nearest star would be so far away that the space between them would feel like an impossible stretch. You could sit and stare at that tiny marble all day, but you'd never get any closer to the nearest star, not in your lifetime, not in any number of lifetimes. This crushing emptiness, this isolation that we feel as we look up at the stars, is not just something that happens when you zoom out from Earth. It is a fundamental part of the universe itself. The space between stars, planets, and galaxies is not just empty. It's an expanse that stretches out into the infinite. The distances involved are so vast that even at the speed of light, which again is the fastest thing we know of in the universe, it would take tens of thousands of years to cross the space between stars. Imagine traveling at the speed of light for your entire life and never even getting close to another star. And then when we zoom out even further, when we start thinking about the scale of our galaxy, the Milky Way, things only get even more unimaginable. Our galaxy, the Milky Way, is home to roughly 400 billion stars, but it's not just the number of stars that's mind-boggling, it's the scale of the galaxy itself. To cross the Milky Way from one side to the other, traveling at the speed of light, would still take you 100,000 years. That's how enormous our home galaxy is. But even this is just the beginning. Beyond our galaxy, there are countless others, each one containing its own set of stars, planets, and potentially life. The number of galaxies in the universe is so vast that we can't even begin to count them all. The universe in its sheer scale dwarfs everything we know. So as we look out into the cosmos, as we peer up into the night sky and try to make sense of the universe, it's easy to get overwhelmed. We see the stars, we see the Milky Way, we see the vast emptiness that surrounds us, and we begin to realize just how small we are, how insignificant we seem in the grand scheme of things. But this feeling, this sense of smallness, is not a reason to despair. Instead, it should be a reason to marvel. Because despite our size, despite our relative insignificance in terms of the cosmos, we are part of something far larger than ourselves, something so vast, so beautiful, and so mysterious that we can't help but wonder what's out there waiting to be discovered. What other secrets of the universe are hidden just beyond our reach, waiting for us to find them? The stars, the galaxies, the cosmic voids, they are not just things to be feared or stared at in awe. They are a part of us, a part of our story, and in understanding them, we understand ourselves. The more we learn about the universe, the more we realize that, while we may be small, we are far from insignificant. We are a part of the great cosmic dance, a small but crucial piece in the vast puzzle of existence. And that, perhaps, is the most amazing thing of all. When we zoom out from Earth, seeing it as a small blue marble in the infinite stretch of space, it's easy to feel insignificant. After all, our planet is tiny compared to the vastness of the cosmos. Yet there's something more remarkable happening beyond our understanding of just how small we are. The universe itself is expanding, and in many ways this expansion is driven by forces and phenomena so massive, so awe-inspiring, that they defy any simple explanation. The scale of this expansion isn't just a curiosity. It is in many ways the very nature of the universe we inhabit. It affects everything from the space between galaxies to the life cycles of stars, planets, and even the fundamental forces that shape reality itself. So when we consider the vast distances separating stars and galaxies, we must also consider something equally mind-boggling: the nature of how those distances are changing. For years, scientists have been measuring the expansion of the universe, and every observation seems to confirm one stunning conclusion: it's accelerating. This means that not only is the universe expanding, but it's doing so at an ever-increasing rate. To picture this, imagine that you're standing in the middle of a balloon. If you draw dots on the surface of the balloon, you'll notice that as you inflate the balloon, the dots move away from each other. The farther apart the dots are, the faster they seem to move apart as the balloon inflates. The same principle applies to the universe, only instead of a balloon, we're talking about the very fabric of space itself, and instead of dots on a surface, we have galaxies, enormous, distant collections of stars, gas, and dust, spreading apart from one another at an accelerating pace. This discovery was nothing short of revolutionary. For decades, astronomers had believed that gravity, the very force that binds stars, planets, and galaxies together, should eventually slow the expansion of the universe. It was the kind of idea that made sense in a world governed by known forces. But the universe had other plans. The evidence for this accelerated expansion came from the observation of distant supernovae. These supernovae, exploding stars in far-off galaxies, served as cosmic beacons that helped scientists measure distances across vast expanses of space. What they found shocked the scientific community. The farther away a galaxy was, the faster it seemed to be moving away from it. And it wasn't just moving away at a steady rate, it was speeding up. To understand this, we have to look at the driving force behind this acceleration. Enter dark energy, a mysterious force that scientists believe is responsible for pushing the universe apart at an ever-increasing rate. Though we can't directly observe dark energy, its effects are unmistakable. It makes up roughly 68% of the universe's total energy content, and it is the dominant force driving the accelerated expansion of space. This force, while invisible and intangible, is one of the most fundamental aspects of our cosmic reality. It is one of the greatest mysteries in science today. But dark energy isn't the only force shaping the universe. There's another cosmic phenomenon that we've only recently come to understand: dark matter. While dark energy is responsible for accelerating the expansion of the universe, dark matter plays a crucial role in the structure and formation of galaxies. Unlike dark energy, dark matter exerts a gravitational pull, and it interacts with normal matter in a way that we can't see, but we can detect through its gravitational effects. Dark matter makes up approximately 27% of the universe's total mass and energy. And while we can't directly observe dark matter, we know it's out there because of the way it affects galaxies. Without dark matter, galaxies would be flying apart. The gravitational influence of dark matter binds galaxies together, creating a cosmic scaffolding that holds galaxies in place. And just like dark energy, dark matter is invisible to our senses. We can't touch it, see it, or interact with it in the conventional sense. Yet it is an essential ingredient in the formation and evolution of galaxies. Both dark matter and dark energy represent some of the most perplexing aspects of the universe. They challenge everything we thought we knew about the cosmos. But these forces, though invisible and difficult to comprehend, are responsible for much of the structure and behavior of the universe. They help shape galaxies, guide the expansion of space, and dictate the way that matter and energy interact on a grand scale. Even as we look outward into the farthest reaches of space, we can't help but feel a sense of awe and wonder at the vastness of what we are observing. But this vastness is not just about space, it's about time as well. When we look out into the cosmos, we're not just seeing stars and galaxies as they are today, we're seeing them as they were millions, even billions of years ago. Light from distant stars takes an incredibly long time to reach us. Some of the stars we observe may have already burned out, exploded, or ceased to exist by the time their light reaches our eyes. What we're really seeing is a snapshot of the past, a glimpse into the history of the universe that's been traveling across space for eons, only now arriving at our corner of the cosmos. This concept of cosmic time adds another layer to the mystery. Just like the Earth has a history, a story that stretches back billions of years, so too does the universe. The light we see from the stars represents a cosmic time machine, one that allows us to peer back into the distant past, to witness events that unfolded long before human beings even existed. When we observe distant galaxies, we're not just observing distant objects in space, we're observing the very history of the universe unfolding before our eyes. And in this vast, ever-expanding universe, we are just one tiny speck of dust. It's easy to feel small when confronted with the scale of the cosmos. It's easy to think that we don't matter, that we're just a fleeting moment in a never-ending expanse of time and space. But that would be a mistake, because even though our planet is tiny, even though our lives are brief in the cosmic scale, the fact that we exist at all is something remarkable. In the face of such an immense universe, we have the capacity to understand it, to study it, and to unravel its mystery. We may be small in the grand scheme of things, but we are part of something much larger than ourselves, and that is the greatest mystery of all. The universe is expanding, dark energy is driving its acceleration, and dark matter is shaping its structure. Every galaxy, every star, and every planet we observe is part of a much grander cosmic story. We are living in a universe that is vast beyond measure, a universe that is constantly changing, evolving, and expanding. And as we continue to study the universe, as we continue to look outward into the vastness of space, we are reminded that we are part of something much larger than ourselves. Even as we continue to explore the mysteries of dark energy and dark matter, we are also exploring the very nature of existence itself, and that journey is only just beginning. As we continue our exploration of the universe, we move beyond the fundamental forces that govern the expansion and structure of the cosmos. Now let's delve deeper into something that's as mysterious as it is awe-inspiring. The stars, these blazing balls of gas, glowing brightly in the night sky, have fascinated humans for millennia. Yet despite their prominence in the universe, stars are far more than just twinkling lights to marvel at from Earth's surface. They are the engines that power the universe, shaping galaxies, fueling the formation of planets, and even providing the raw materials for life itself. But the story of stars is much more than just their brilliance. It's a story of creation, transformation, and eventual death. To understand the significance of stars, we need to look at their life cycles. At the heart of every star is a process known as nuclear fusion, which occurs when the star's core becomes so hot and dense that it forces atoms to fuse together, releasing an enormous amount of energy. This energy radiates outward, causing the star to shine brilliantly, lighting up entire regions of space. But this shining isn't eternal. Just like every living organism, stars have a lifespan, a period during which they shine and perform their functions before eventually dying. The first stage in a star's life is what we call the protostar phase. This is when a cloud of gas and dust pulled together by gravity begins to collapse inward, forming a dense core. As the core compresses, it heats up, and eventually nuclear fusion begins. This marks the birth of a star. The newly formed star is incredibly hot, and it begins to shine as its energy escapes into space. At this point, the star begins its long journey through the stages of its life, with the balance between the force of gravity pulling inward and the energy from fusion pushing outward, determining its stability. From here, stars enter what is known as the main sequence phase. This is where most stars, including our own Sun, spend the majority of their lives. The main sequence phase is characterized by steady fusion, with hydrogen atoms fusing into helium in the star's core. This fusion process generates the energy that powers the star and keeps it shining. For stars like our Sun, this phase can last for billions of years, but all stars eventually exhaust the hydrogen fuel in their cores, which leads to the next phase in their life cycle, the red giant phase. As a star runs out of hydrogen, its core begins to collapse under the force of gravity, while the outer layers expand. This causes the star to cool and turn red, giving it the characteristic appearance of a red giant. In this phase, the star begins fusing heavier elements, such as helium, into even heavier elements like carbon and oxygen. But this phase is short-lived compared to the main sequence phase. As the star continues to fuse heavier and heavier elements, it grows unstable. In the final stages of a star's life, the core can no longer sustain the fusion reactions, and the star begins to shed its outer layers, creating a stunning and dramatic display known as a planetary nebula. The core that remains behind can either collapse into a white dwarf, a dense remnant of the star that will eventually cool and fade over the course of billions of years, or, in the case of more massive stars, the core can collapse under its own gravity to form a neutron star or even a black hole. This cataclysmic death, known as a supernova, is one of the most powerful explosions in the universe. A supernova releases an immense amount of energy, scattering the star's outer layers into space, enriching the surrounding regions with heavy elements like iron and gold, elements that are crucial for the formation of planets. And ultimately, but the death of a star is not the end. In fact, it's just the beginning of a new chapter in the story of the universe. The heavy elements scattered by supernovae become the building blocks for new stars, planets, and even life. These elements, like carbon and oxygen, are the very same ones that make up our bodies, the air we breathe, and the world we live on. The process of star formation and star death is a cycle that is crucial to the creation of everything in the universe. Consider the fact that when our sun eventually reaches the end of its life and expands into a red giant, it will shed its outer layers, and these layers will contribute to the formation of new stars and planets in the surrounding space. This process, known as stellar recycling, ensures that the universe is constantly creating new stars and new possibilities for life. Every star that has ever lived and died has played a part in this cosmic cycle. The atoms that make up our bodies were once part of a star that lived and died billions of years ago, and this link between the stars and life on Earth creates a sense of connection between us and the entire universe. This understanding of stars and their life cycles brings a new perspective on our place in the cosmos. When we look up at the night sky, we aren't just looking at distant points of light. We're looking at the remnants of stars that have lived and died, some of them long before humanity ever existed. We are seeing the history of the universe unfold before our eyes. And yet, even as we peer into the past, the stars continue their cycles, creating the elements necessary for the formation of new worlds, new possibilities, and even new life. The universe is constantly evolving, driven by the cycles of birth, death, and rebirth that are the essence of the stars. But stars don't just give us elements. They also provide the energy that sustains life on Earth. The Sun, our nearest star, is the source of all life on Earth. Its light and warmth are essential for the existence of life as we know it. The energy that the Sun provides is what drives our climate, our weather, and even our ecosystems. Without the Sun, there would be no life on Earth, and no possibility for the complex web of organisms that inhabit our planet. And while the Sun is the star that directly affects our lives, it is just one of countless stars scattered across the universe. Many of these stars are similar to our Sun, and some are even more massive, burning brighter and hotter than our star. These stars can form in clusters, where dozens, even hundreds of stars are born in the same region of space. These stellar nurseries, as they are known, are regions of intense gravitational collapse, where clouds of gas and dust collapse under their own weight to form new stars. Yet, not all stars live peaceful lives. Some engage in a cosmic dance with other stars, forming binary systems where two stars orbit each other in a delicate balance of gravitational forces. In these systems, the stars can exchange mass, causing one star to grow hotter and more massive, while the other dims and cools. The interactions between these stars can create dramatic and beautiful phenomena, like the formation of novas, which are sudden bursts of energy caused by the explosion of material from one star onto the surface of a companion star. Beyond binary systems, there are also star clusters, where stars form in groups and are bound together by gravity. These clusters can contain hundreds or even thousands of stars, all born from the same cloud of gas and dust. The stars in these clusters are often similar in age, size, and composition, giving astronomers valuable insights into the processes of stellar formation and evolution. The study of star clusters, both near and far, has helped us understand not only the nature of stars but also the conditions that led to the formation of galaxies, planets, and life itself. The life of a star, from its birth to its death, is a story of transformation. It is a story that mirrors the broader processes of creation and destruction that govern the universe. Stars are the forges in which the elements that make up our world are created. They are the engines that power the universe, driving the formation of planets, stars, and galaxies. And in their death, they provide the raw materials for the next generation of stars and planets. Every star that has ever lived, from the smallest red dwarf to the largest supergiant, has played a part in this cosmic story. And we, as part of this universe, are intrinsically connected to the stars, to their life cycles, and to the story of creation that has unfolded over billions of years. As we stand at the threshold of space, gazing up at the stars, it's easy to get lost in the beauty of the cosmos. The vast expanse of the universe, with its countless galaxies, stars, and planets, can feel overwhelming, almost beyond comprehension. Yet, in the midst of all this grandeur, one truth becomes strikingly clear. The universe is not static. It is alive, dynamic, and ever-changing. The forces that shape the universe are vast, intricate, and at times bewildering. One of the most profound of these forces is gravity, the unseen hand that guides the motion of every planet, star, and galaxy in existence. But gravity is not the only force at work. There are other, more mysterious forces that govern the cosmos, ones that we are only beginning to understand. The most enigmatic of these are the forces of dark matter and dark energy, forces that dominate the universe in ways that challenge our very understanding of the laws of physics. Dark matter is, in many ways, the hidden scaffolding of the universe. Though we cannot see it, feel it, or interact with it directly, we know it exists because of its gravitational effects on visible matter. In fact, dark matter makes up about 27% of the total mass and energy content of the universe. It doesn't emit, absorb, or reflect light, which is why it's completely invisible to us. But its influence is undeniable. It is the glue that holds galaxies together. Without dark matter, galaxies would fly apart. The stars within them would not be bound by gravity in the way they are. The very structure of the universe as we know it would collapse. The concept of dark matter was first proposed in the 1930s, when astronomer Fritz Zwicky observed the motion of galaxies within clusters. He noticed that the galaxies were moving much faster than could be explained by the amount of visible matter in the clusters. The only way to account for their high velocities was to assume that there was some invisible, unseen mass providing additional gravitational pull. Since then, scientists have detected dark matter in many other ways, primarily through its gravitational effects on visible matter. The most compelling evidence for dark matter comes from the observation of galaxy rotation curves. When we look at the way galaxies rotate, we expect that the outer stars in a galaxy should move more slowly than the stars near the center, because there is less visible matter to provide gravitational pull. But in reality, the outer stars are moving just as fast as those near the center, which suggests that there is a large amount of unseen mass at work. This invisible mass is what we call dark matter. Despite its pervasive influence, we still know very little about the true nature of dark matter. It does not interact with electromagnetic radiation, that is, it doesn't emit, absorb, or reflect light, making it completely invisible to our telescopes. It doesn't seem to interact with ordinary matter except through gravity. It is, quite literally, a mystery that eludes our most powerful instruments, and yet we know it is there, shaping the structure of the universe, influencing the formation of galaxies, and even determining the behavior of galaxy clusters. Without dark matter, the universe would look very different. The galaxies would not have formed in the way they did, and the vast cosmic structures we see today might never have existed. But dark matter is not the only mysterious force in the universe. There is another force, one that is even more puzzling: dark energy. Dark energy is the name given to the force that is driving the accelerated expansion of the universe. It is thought to make up about 68% of the total energy content of the universe, making it the dominant force in the cosmos. And yet, just like dark matter, we know very little about what dark energy actually is. The discovery of dark energy came in 1998, when astronomers were studying the light from distant supernovae. These supernovae, which occur when massive stars explode, are used as standard candles to measure distances across the universe. By studying the brightness of these supernovae, astronomers can determine how far away they are. But when they observed the most distant supernovae, they found something unexpected. The light from these supernovae was fainter than they had anticipated, suggesting that the expansion of the universe was accelerating rather than slowing down as they had expected. This discovery led to the realization that there was some mysterious force later dubbed dark energy, pushing galaxies apart at an ever-increasing rate. Unlike dark matter, which works through gravity, dark energy appears to have a repulsive effect. It acts like a kind of anti-gravity, pushing galaxies away from each other. The exact mechanism behind dark energy is still unknown, but its effects are undeniable. It is responsible for the accelerated expansion of the universe, a phenomenon that has been observed in many different regions of space. The discovery of dark energy has fundamentally changed our understanding of the universe. For decades, scientists had thought that gravity would eventually slow the expansion of the universe, but dark energy has shown us that the opposite is true. The universe is not just expanding, it is expanding faster and faster with each passing moment. One of the most mind-boggling aspects of dark energy is its sheer power. Despite making up nearly 70% of the total energy content of the universe, We have no idea what dark energy is made of, how it works, or even why it exists. Some scientists speculate that it may be a property of space itself, a kind of vacuum energy that arises from the quantum fluctuations of empty space. Others believe that it could be a manifestation of a new kind of force, one that operates on the largest scales of the universe. Whatever the true nature of dark energy turns out to be, it is clear that it is the dominant force in the universe today, and it will continue to shape the fate of the cosmos for billions of years to come. As we look out into the universe, we are confronted with these two great mysteries, dark matter and dark energy. Together, they make up over 95% of the total mass and energy content of the universe, and yet we know so little about them. They are invisible, intangible, and elusive, defying our understanding of the fundamental laws of physics. And yet, they are the forces that govern the cosmos, shaping everything from the formation of galaxies to the expansion of space itself. They remind us that despite all our knowledge, the universe is still full of mysteries waiting to be unraveled. But even as we strive to understand the forces of dark matter and dark energy, we are also confronted with another, more immediate question. What is our place in all of this? When we look at the vastness of the cosmos, it's easy to feel insignificant, to think that we are just a tiny speck in an immense indifferent universe. But the more we learn about dark matter, dark energy, and the forces that shape the universe, the more we realize that we are part of something much larger than ourselves. The same forces that created the stars, that formed galaxies, and that drive the expansion of the universe also shaped our existence. We are made of the very elements that were created in the hearts of stars. Our planet, our solar system, and our galaxy are the product of billions of years of cosmic evolution. The universe is not just a vast empty expanse. It is a living, breathing entity, constantly changing and evolving, and we are a part of that process. As we continue to explore the mysteries of dark matter and dark energy, we are reminded that we are not just passive observers of the cosmos. We are active participants in the unfolding story of the universe. The universe is not indifferent to us. It is in many ways our cosmic home, and we are bound to it in ways that we are only beginning to understand. The more we learn about the forces that shape the universe, the more we realize that we are intricately connected to it. The story of dark matter and dark energy is not just the story of the universe. It is our story too. And as we continue to explore the mysteries of the cosmos, we are not just uncovering the secrets of the universe, we are uncovering the secrets of ourselves. As we stand here on Earth, looking up at the stars, it's easy to get swept up in their beauty and majesty. The stars seem so distant, so unattainable, twinkling in the sky like beacons from a far-off world. Yet, beneath the surface of this cosmic spectacle lies a truth that is far more profound. The stars are not just distant points of light in the night sky, they are the lifeblood of the universe, the engines that drive everything we know. The existence of stars, their formation, their life cycles, and their eventual death all play crucial roles in shaping the very fabric of the cosmos. In fact, the stars are the architects of everything we see around us, from the elements in our bodies to the very structure of galaxies. It is often said that we are stardust. This poetic phrase carries a deep truth about our origins. The atoms that make up our bodies, the earth beneath our feet, and even the air we breathe were all forged in the hearts of ancient stars. But how do these stars come to life in the first place? And what drives their incredible energy? The birth of a star begins in a dense, cold cloud of gas and dust, which we call a nebula. These nebula are the cosmic nurseries where new stars are born. Over time, gravity begins to pull the particles within the nebula together, causing the cloud to contract and heat up. As the pressure in the core of the cloud increases, nuclear fusion reactions start to occur, and a star is born. This early stage is marked by intense heat and light, as hydrogen atoms fuse together to form helium, releasing massive amounts of energy. This marks the beginning of the star's main sequence phase, the stage where it will spend most of its life. For stars like our Sun, the main sequence phase lasts billions of years. During this time, the star maintains a delicate balance between the inward pull of gravity, which wants to collapse the star, and the outward pressure from the energy produced by nuclear fusion, which wants to push the star apart. It's this balance that allows the star to remain stable for such an extended period. For stars like the Sun, the primary fuel is hydrogen, which is converted into helium in the star's core. This process produces immense amounts of energy, which radiates outward, providing the light and heat that make life on Earth possible. However, stars' time on the main sequence is not infinite. Eventually, the hydrogen in the core will run out, and the star will begin to change. As fusion slows down in the core, gravity causes the core to contract, and the outer layers expand. This marks the beginning of the star's transformation into a red giant. In this phase, the star begins fusing heavier elements like helium into carbon and oxygen. The star becomes much larger and cooler, and its outer layers may even expand to the point where they engulf nearby planets, like Mercury and Venus. While this is an awe-inspiring spectacle, it's also a sign that the star is reaching the end of its life. The eventual fate of a star depends on its mass. Smaller stars like our Sun will shed their outer layers, creating a beautiful cloud of gas and dust known as a planetary nebula. The core that remains behind will become a white dwarf, a small dense remnant of the star that will slowly cool over billions of years. While it won't produce any more energy, the white dwarf will remain as a silent, fading relic of the star's once great power. For more massive stars, the death of the star is far more dramatic. When a massive star reaches the end of its life, it can no longer sustain nuclear fusion in its core. The pressure from the fusion reactions can no longer counteract the pull of gravity, and the core collapses in on itself, creating a massive explosion known as a supernova. This explosion releases an incredible amount of energy, briefly outshining the entire galaxy and scattering the star's outer layers into space. The remnants of the star's core may form a neutron star or, in the case of the most massive stars, collapse further into a black hole. The death of a star is a violent and dramatic event, but it is also one of the most important processes in the universe. The energy released in a supernova can trigger the formation of new stars, and the elements created in these explosions are spread throughout the cosmos. Elements like carbon, oxygen, and iron, the building blocks of life, are created in the cores of stars and spread into space when those stars die. These elements are eventually incorporated into new stars, planets, and even living organisms. Without the death of stars, there would be no life as we know it. We are, quite literally, made of star stuff. Beyond their creation of elements, stars also shape the very structure of the universe. The gravitational pull of stars and galaxies affects the way that galaxies form and evolve. Stars are not solitary objects. They are part of vast cosmic structures known as galaxies. A galaxy is a collection of stars, gas, dust, and dark matter, all bound together by gravity. There are billions of galaxies in the universe, each with billions of stars. These galaxies are not static. They are constantly moving, interacting, and evolving. One of the most profound discoveries in modern astronomy is the realization that galaxies are not just isolated objects, but are part of a much larger cosmic web. Galaxies are connected by vast filaments of dark matter, creating a cosmic web that stretches across the universe. This web, which is made up of both visible and invisible matter, dictates the motion and structure of galaxies. The stars within these galaxies move according to the gravitational influence of the dark matter, and the movement of galaxies themselves is influenced by the vast gravitational currents that flow through the cosmic web. The life cycle of stars is not just a story of birth, growth, and death. It is also a story of interconnectedness and recycling. When a star dies, it does not simply vanish. Instead, it releases its material back into the universe, enriching the interstellar medium with the elements necessary for the formation of new stars and planets. This process, known as stellar nucleosynthesis, ensures that the elements necessary for life, carbon, oxygen, nitrogen, and iron, are spread throughout the universe, providing the raw materials for the next generation of stars, planets, and life forms. In this way, stars are the ultimate recyclers. They are born, live, die, and then return their material to the cosmos, allowing the cycle of creation and destruction to continue. This cycle has been going on for billions of years, and it will continue for billions more. Stars are not just the sources of light and heat. They are the engines that drive the evolution of the universe, shaping the cosmos through their formation, life, and death. As we gaze up at the night sky, we are looking at the past. The light from the stars we see tonight has traveled for millions, even billions of years to reach us. Some of the stars we see may no longer exist, their light still traveling across space long after they have burned out or exploded. In this way, the stars serve as a kind of time machine, allowing us to peer back into the history of the universe. The light we see tonight is not just a reflection of the present, it is a glimpse into the distant past, a reminder of the long history of star formation, evolution, and death that has shaped the cosmos. The stars are the architects of the universe. They are the creators of the elements, the builders of galaxies, and the catalysts for the formation of life. Their life cycles, from birth to death, shape the very structure of the cosmos, and as we continue to study the stars, we continue to uncover the mysteries of the universe, learning more about the forces that govern the cosmos and our place within it. The story of the stars is the story of the universe itself, and in that story we are all participants. We are stardust, and our lives are inextricably linked to the cycles of creation and destruction that have been unfolding in the cosmos for billions of years. As we look deeper into the cosmos, one of the most captivating aspects of our universe is its complexity. This complexity isn't just limited to the grand scales of galaxies and stars, but also exists in the intricate invisible structures that weave the very fabric of the cosmos together. One such mystery that continues to intrigue and mystify scientists is the concept of the supermassive black hole. These colossal entities lie at the centers of many galaxies, including our own Milky Way. Their presence shapes the structure and dynamics of entire galaxies and has profound implications for our understanding of space, time, and the very nature of reality itself. Black holes in general are fascinating objects. They form when massive stars collapse under their own gravity, compressing their mass into a point of infinite density known as a singularity. The force of gravity is so intense near this point that not even light can escape, which is why they're called black holes. But while the idea of black holes has long captured the human imagination, it's the supermassive black holes that truly redefine our understanding of the universe. These supermassive black holes are not the result of a single star's collapse, but rather the accumulation of mass over billions of years. At the heart of many galaxies, including our own, lies a supermassive black hole with a mass ranging from millions to billions of times that of our Sun. The one at the center of the Milky Way, known as Sagittarius A, has a mass about 4 million times that of the Sun. And yet, despite their immense size, these black holes occupy an incredibly small volume of space. It's their gravitational pull, however, that makes them so fascinating and so crucial to the structure of galaxies. To understand why these supermassive black holes are so significant, we need to explore their role in the dynamics of galaxies. Observations of galaxies reveal that they tend to have a close correlation between their size, shape, and the mass of the supermassive black hole at their core. In fact, this relationship is so consistent that scientists believe supermassive black holes may play a key role in the formation and evolution of galaxies themselves. But how exactly do these enormous objects influence the galaxies they inhabit? One theory is that the presence of a supermassive black hole at the center of a galaxy acts as a kind of anchor, helping to hold the galaxy together and maintain its shape. The black hole's immense gravitational pull influences the movement of stars and gas clouds in the galaxy, stabilizing the galaxy's structure and ensuring that it doesn't break apart over time. Without the gravitational force exerted by these supermassive black holes, galaxies might not form or evolve in the way that we see them today. But the influence of supermassive black holes goes beyond just maintaining the galaxy's structure. In fact, they are also thought to play a critical role in regulating the growth of the galaxy itself. In the centers of galaxies, gas clouds and dust fall toward the supermassive black hole, fueling its growth. However, as matter approaches the event horizon, the point of no return, it gets heated up to extreme temperatures, emitting vast amounts of energy in the process. This radiation creates powerful winds and outflows of gas that can blow away the surrounding material, essentially halting further growth of the black hole and the galaxy itself. This phenomenon, called feedback, is thought to be responsible for regulating the rate at which galaxies form stars. When a supermassive black hole becomes too active, producing too much radiation and driving away gas, it can suppress the formation of new stars, slowing the growth of the galaxy. Conversely, when the black hole is quiet and inactive, the surrounding gas can accumulate, fueling star formation and allowing the galaxy to grow. In this way, supermassive black holes act as both the engines and regulators of galaxy formation, balancing the forces of creation and destruction within the cosmic ecosystem. But perhaps the most mind-blowing aspect of supermassive black holes is their ability to warp space and time itself. The general theory of relativity proposed by Albert Einstein in 1915 describes how massive objects like black holes warp the fabric of space-time around them. This warping causes light and matter to bend in ways that can be observed and measured. Near a supermassive black hole, space and time become so warped that they behave in ways that are impossible to experience anywhere else in the universe. One of the most famous predictions of general relativity is that light traveling near a black hole or bend around it due to the distortion of space-time. This effect, called gravitational lensing, can be observed when light from distant stars or galaxies passes close to a supermassive black hole. The black hole's gravity bends the light, magnifying and distorting the image of the object behind it. This phenomenon not only confirms the predictions of general relativity, but also gives scientists a powerful tool to study objects that would otherwise be invisible, including the black holes themselves. Another mind-boggling consequence of a supermassive black hole's warping of space and time is the time dilation effect. According to general relativity, time moves more slowly the closer you get to a massive object. So, if you were to approach a supermassive black hole, time would appear to slow down relative to someone far away from the black hole. This means that, in theory, if you were to get close enough to the event horizon, time would nearly come to a halt for you, while the rest of the universe would continue to move forward as normal. The implications of this are profound. Not only does it challenge our understanding of time and space, but it also opens the door to new possibilities for studying the most extreme environments in the universe. But despite their powerful influence, supermassive black holes remain incredibly elusive. These objects are notoriously difficult to study because they don't emit light or radiation in the traditional sense. Most of what we know about black holes comes from indirect observations, such as the movement of nearby stars and the radiation emitted as matter is sucked into the black hole. However, recent advancements in observational techniques are giving us new insights into the behavior of these mysterious objects. One of the most exciting developments in black hole research is the Event Horizon Telescope, EHT, a global network of radio telescopes that came together in 2019 to capture the first ever image of a black hole. This historic image, taken of the supermassive black hole at the center of the galaxy M87, was a monumental achievement in the study of black holes. For the first time, scientists were able to directly observe the shadow of a black hole, the dark region surrounded by a glowing halo of hot gas. This groundbreaking image not only provided conclusive evidence of the existence of supermassive black holes, but also opened up new possibilities for studying the nature of these enigmatic objects. But the EHT image is just the beginning. As technology continues to advance, astronomers are developing even more sophisticated instruments to study supermassive black holes in greater detail. With the advent of next-generation telescopes, such as the James Webb Space Telescope JWST, set to launch soon, scientists hope to gain a deeper understanding of the behavior of black holes, their role in galaxy formation, and their influence on the evolution of the universe. Despite the progress we've made in studying supermassive black holes, there is still much to learn. How do these objects form in the first place? What is the precise mechanism behind their incredible power? And what lies at the heart of a supermassive black hole? What happens to matter and energy once it crosses the event horizon? These questions remain some of the greatest mysteries in modern astrophysics. One thing is certain, however: supermassive black holes are not just bizarre oddities of the cosmos. They are fundamental to our understanding of the universe itself. Their role in shaping galaxies, their ability to warp space and time, and their capacity to reveal the limits of our understanding of physics make them key players in the grand narrative of the cosmos. As we continue to explore these mysterious objects, we are not just peering into the darkness at the heart of galaxies, we are peering into the very heart of the universe's most profound secrets. When we think about the universe, we often imagine vast galaxies, shimmering stars, and swirling nebulas. These grand cosmic structures capture our attention and fill us with awe. But beyond these visible wonders lies an even deeper mystery that affects every corner of the universe: the true size and scale of the galaxies themselves. One of the most fascinating revelations in modern astronomy is just how large the universe really is, particularly when we zoom out far enough to understand the sheer scope of a galaxy and its size relative to others. Galaxies are not only the basic building blocks of the universe, but are also incredibly diverse in size, structure, and mass, each with its own distinct features and history. Understanding the size of galaxies and how they fit into the larger picture of the cosmos helps us better comprehend the universe's formation and the forces that have shaped it over billions of years. At the heart of every galaxy, regardless of its size or shape, lies a supermassive black hole. These enormous gravitational wells act as the central engine that drives the motion of stars, gas, and dust within the galaxy. And yet, the galaxy itself is far more than just the sum of its black hole and its stars. The galaxy is a vast collection of matter, billions, sometimes even trillions of stars, planetary systems, nebulae, and interstellar gas, all bound together by gravity. These cosmic structures are as varied as they are numerous, with some galaxies sprawling across hundreds of thousands of light years, while others are relatively compact. The Milky Way, our own home galaxy, is a barred spiral galaxy. It's massive, spanning about 100,000 light-years across, and contains hundreds of billions of stars, including our Sun. But as we begin to explore the true scale of the universe, we realize that the Milky Way is not the largest galaxy in our cosmic neighborhood. In fact, it's far from the biggest or most massive. There are many other galaxies, some far larger and more complex than our own. One of the largest and most notable galaxies in our local group is the Andromeda Galaxy, also known as M31. This spiral galaxy is similar in structure to the Milky Way, but is roughly 2.5 million light-years away and is on a collision course with our galaxy. In a few billion years, the Milky Way and Andromeda will merge, forming an entirely new larger galaxy, perhaps an elliptical galaxy, a result of this monumental cosmic collision. The size of a galaxy is often determined by its mass and the amount of matter it contains. The largest galaxies in the universe are known as giant elliptical galaxies. These enormous galaxies, which can span up to 1 million light-years in diameter, are packed with stars, often hundreds of trillions of them. What makes these galaxies so fascinating is that they don't just represent an anomaly in size. They also tell us a great deal about the evolution of the universe. Giant elliptical galaxies tend to be older, often formed by the merging of smaller galaxies. The large size of these galaxies is partly due to the gravitational collapse of gas and dust, which condenses into stars and clusters, allowing them to become the massive objects we observe today. In contrast, dwarf galaxies are much smaller, often just a few thousand light-years across. Despite their size, they can contain millions or billions of stars, making them smaller than the Milky Way by orders of magnitude. Though they may seem insignificant compared to their larger counterparts, dwarf galaxies are still important in understanding the evolution of the universe. Many dwarf galaxies are believed to be the building blocks of larger galaxies, remnants of earlier cosmic structures that have yet to merge with other galaxies to form larger systems. But what truly sets galaxies apart from one another is their structure. Galaxies come in a variety of shapes: spiral, elliptical, irregular, and the spiral galaxies, such as the Milky Way and Andromeda, have a distinct structure that includes a central bulge, a flat disk with spiral arms, and a halo of older stars and globular clusters. The spiral arms are areas of intense star formation, filled with young, hot stars and nebulae. The central bulge, by contrast, is typically populated with older stars and a supermassive black hole at the core, which helps stabilize the galaxy's shape. Elliptical galaxies, on the other hand, are more featureless and round or elongated in shape, without the distinctive spiral arms. These galaxies contain mostly older stars and have little to no star formation occurring in their centers. They are often the result of galaxy mergers, where the gravitational forces between two galaxies cause them to collide and merge, ultimately resulting in an elliptical galaxy. These mergers are some of the most dramatic and violent events in the universe, and they play a key role in the growth and evolution of galaxies. Despite their lack of star formation, elliptical galaxies often contain a significant amount of dark matter, which accounts for a large portion of their mass. Irregular galaxies are another intriguing category, characterized by their chaotic, non-symmetrical shapes. These galaxies often lack the well-defined structure of spiral or elliptical galaxies, and are typically smaller. Irregular galaxies are often the result of gravitational interactions with other galaxies, and they can be a stage in the evolutionary process of a galaxy as it interacts with its surroundings. They are also a key indicator of the dynamic and ever-changing nature of the universe, as they provide insight into the complex forces that shape galaxies over time. One of the most important aspects of galaxies, regardless of their shape, is the way they interact with each other. Galaxies are not isolated entities floating in space. They are part of a vast cosmic web of interconnected structure. The gravitational forces between galaxies can lead to a variety of phenomena, including galaxy mergers, tidal interactions, and the formation of galaxy clusters. In fact, the largest structures in the universe, galaxy clusters, are composed of hundreds or thousands of galaxies bound together by gravity. These clusters provide a unique opportunity to study the large-scale structure of the universe and the interplay between galaxies. One of the most famous galaxy clusters is the Virgo cluster, which contains more than 2,000 galaxies, including many massive elliptical galaxies. Galaxy clusters are important because they help us understand how galaxies form and evolve. The interactions between galaxies in a cluster can lead to phenomena like galactic cannibalism, where a larger galaxy absorbs a smaller one, and the stripping of gas from galaxies, which can halt star formation and cause galaxies to dry up. But while the study of galaxies provides crucial insights into the universe's evolution, one of the most fascinating aspects of galaxies is how they fit into the larger scale of the universe. Galaxies are not just isolated structures, they are part of a vast cosmic tapestry, interconnected by the forces of gravity and the mysterious web of dark matter. This web stretches across the universe, linking galaxies into larger structures, such as superclusters and voids. A supercluster is a massive collection of galaxy clusters, and these superclusters form the largest known structures in the universe. The Laniakea supercluster, which includes our own Virgo cluster, is an example of this vast structure, stretching over 520. But galaxies aren't just bound together in large clusters, they are also constantly moving through space. The motion of galaxies is governed by the expansion of the universe itself. The universe has been expanding since the Big Bang, and this expansion continues today. The cosmic microwave background radiation, which is the afterglow of the Big Bang, provides evidence for this expansion and has allowed scientists to measure the rate at which galaxies are moving apart. This expansion is driven by dark energy, a mysterious force that pushes galaxies apart, accelerating the expansion of the universe. As galaxies move apart, they also continue to interact with each other, sometimes colliding or merging, creating new galaxies and triggering the formation of stars. The understanding of galaxy sizes, shapes, and their evolution is an ongoing journey for astronomers. With each new discovery, we gain a clearer picture of how the universe has evolved over the past 30. Modern telescopes, like the James Webb Space Telescope, are providing us with unprecedented views of distant galaxies, allowing us to peer back in time and observe galaxies as they were billions of years ago, shortly after the birth of the universe. These observations are giving us vital clues about the processes that led to the formation of galaxies, stars, and planets, and ultimately to the conditions that made life possible. Yet, even with all the advancements in technology, we have only begun to scratch the surface of understanding the true scale of galaxies and their role in the universe. The vastness of the cosmos, the incredible diversity of galaxies, and the mysterious forces that shape them all point to a universe that is far more complex and interconnected than we can fully comprehend. Each new discovery adds another piece to the cosmic puzzle, bringing us one step closer to understanding the universe's past, present, and future. But in many ways, the journey is just beginning. And as we look deeper into the cosmos, one thing is certain: there are still many more mysteries waiting to be unraveled. The journey through the cosmos continues to reveal one awe-inspiring truth. The universe, with all its vastness and complexity, is in constant motion. Galaxies, stars, and even planets are not fixed. They are all part of an ongoing cosmic ballet, moving, interacting, and evolving across time. Yet, despite this overwhelming sense of cosmic dynamism, there are forces at play that seem to defy the ordinary rules of motion. Forces so large and so powerful that they shape the entire structure of the universe. One such force is the mysterious and seemingly invisible force known as dark energy, which is driving the accelerated expansion of the universe. However, there's another phenomenon, even more fundamental to the way galaxies interact, that's been quietly shaping the universe for billions of years: the gravitational pull of supermassive black holes and the gravitational anomalies known as the Great Attractor. The Great Attractor is a name given to an enigmatic region of space that seems to exert a massive gravitational force on galaxies across a vast section of the universe, drawing them toward it. Yet despite its profound influence, the Great Attractor itself remains largely invisible. We cannot directly observe it because it lies behind the zone of avoidance, a region of space densely populated with stars, gas, and dust in the Milky Way's plane, which blocks our line of sight. This makes the Great Attractor one of the most elusive objects in cosmology. Still, its influence is undeniable, and understanding it offers profound insights into the structure of the universe and the forces that govern it. The existence of the Great Attractor was first hinted at in the 1970s when astronomers noticed that galaxies within a specific region of the sky were all moving toward a common point, as if pulled by some unseen gravitational force. Initially, astronomers were puzzled by this observation, as they had no explanation for the motion of these galaxies. It wasn't until the early 1990s that the term Great Attractor was coined, as the motion of galaxies could not be explained by the known mass of matter in the region. Something far more massive and unseen must be at work. Since then, astronomers have worked diligently to map out the motions of galaxies in the direction of the Great Attractor, uncovering a vast, complex web of gravitational interactions that extend across hundreds of millions of light-years. The Great Attractor itself appears to be located at the center of a massive gravitational anomaly known as the Laniakea supercluster, which contains not only the Milky Way, but also thousands of other galaxies. It is a region of immense cosmic influence that pulls galaxies toward it, with our own galaxy, the Milky Way, part of this motion as it moves toward the Great Attractor at speeds of around 600 kilometers per second. What is the Great Attractor? It's a question that remains largely unanswered. While scientists have speculated that it could be a concentration of galaxies, a massive cluster of dark matter, or even a supermassive black hole, its true nature is still unclear. One of the challenges in studying the Great Attractor is that, due to its location behind the zone of avoidance, we cannot easily observe it. The dense clouds of stars and gas in the Milky Way's plane obscure our view, making it difficult to discern exactly what lies at the heart of this powerful gravitational anomaly. However, the gravitational effects of the Great Attractor are so profound that they can't be ignored, even though we can't directly see what's causing them. Despite the challenges in directly observing the Great Attractor, scientists have made significant progress in mapping out the region around it. Using sophisticated techniques such as redshift surveys, astronomers have been able to measure the velocity of galaxies in the direction of the Great Attractor. These measurements show that galaxies are being drawn toward this mysterious region of space, moving at speeds that are far greater than what would be expected from the gravitational influence of the visible matter in the area. This suggests that there is far more mass in the region than we can currently observe, likely in the form of dark matter, which could be contributing to the gravitational pull that drives the motion of galaxies. In addition to this, the Great Attractor is also closely tied to a larger structure in the universe known as the Cosmic Microwave Background, CMB, which is the afterglow of the Big Bang. The CMB is a faint radiation that permeates the entire universe and provides a snapshot of the universe as it was just 380,000 years after the Big Bang. Interestingly, the motion of galaxies toward the Great Attractor seems to be reflected in the CMB itself. This observation has led scientists to hypothesize that the Great Attractor could be part of an even larger structure, one that is exerting a gravitational influence on the entire observable universe. To understand the significance of this, it's important to consider the larger context of cosmic structure. The universe is not a random scattering of galaxies. Instead, it has a complex web-like structure, with galaxies connected by vast filaments of dark matter. This structure is known as the cosmic web, and it is thought to be the result of the gravitational pull exerted by dark matter. The Great Attractor, in this sense, is not an isolated anomaly. Rather, it is a key component of a much larger cosmic structure, one that is responsible for the formation and distribution of galaxies across the universe. In addition to the gravitational forces of the Great Attractor, the universe itself is expanding. This expansion, first discovered by Edwin Hubble in the 1920s, has been confirmed by numerous observations since. The expansion of the universe means that galaxies are moving away from each other, and this effect is observable in the redshift of light from distant galaxies. However, despite the general expansion of the universe, regions like the Great Attractor demonstrate that the motion of galaxies is not uniform. In some regions, the gravitational forces of large structures are pulling galaxies together, causing them to move toward each other rather than away. This complex interplay between the expansion of the universe and the gravitational forces exerted by large structures like the Great Attractor adds a layer of complexity to our understanding of cosmic evolution. What does all of this mean for the future of the universe? The influence of the Great Attractor on galaxies and the expansion of the universe suggests that our understanding of cosmic dynamics is still incomplete. While the expansion of the universe is accelerating due to the influence of dark energy, the gravitational pull of massive structures like the Great Attractor suggests that the universe is not simply expanding uniformly. This raises the possibility that the fate of the universe could be influenced by large, unseen structures like the Great Attractor. One of the key questions that remains is whether the influence of structures like the Great Attractor will eventually lead to a reversal of the universe's expansion. Will the gravitational pull of these large structures one day overcome the effect of dark energy, causing the universe to contract and leading to a big crunch? Or will dark energy continue to drive the accelerated expansion of the universe, pushing galaxies farther and farther apart for eternity? The answer to this question depends on our understanding of dark energy, dark matter, and the large-scale structure of the universe, mysteries that are still very much unsolved. In the end, The Great Attractor is a reminder that the universe is full of forces and phenomena that we don't yet fully understand. While it remains one of the most enigmatic and elusive objects in the cosmos, the study of its gravitational influence is helping to reveal the structure of the universe and the forces that shape it. As our technology improves and we gain new tools to peer deeper into the cosmos, we may eventually unravel the secrets of the Great Attractor and other mysterious structures like it. But for now, it remains one of the many profound mysteries that fuel our curiosity and inspire our exploration of the vast, interconnected universe we call home. As we look out into the night sky, the vastness of the universe is immediately apparent. The stars, though they appear as mere twinkling points of light from our vantage point on Earth, are actually enormous balls of gas burning at unimaginable temperatures, many light years away. Beyond these stars lies an intricate network of galaxies, each one home to billions, sometimes trillions, of stars. Some of these galaxies are so far away that their light takes millions, even billions, of years to reach. And yet, despite the overwhelming sense of scale, our understanding of the cosmos is still in its early stages. One of the most intriguing and fundamental aspects of the universe is its age, a concept that has fascinated scientists and philosophers for centuries. At the heart of our understanding of the universe's age is the Big Bang theory, which posits that the universe began as an infinitely small, hot and dense point approximately 13.8 billion years ago. This event marked the birth of space, time and matter as we know them. From this singularity, the universe began to expand, and over billions of years, matter began to coalesce into galaxies, stars and planets. But while the Big Bang offers a framework for understanding the universe's origins, measuring its age involves a combination of theoretical models, observational data, and a range of scientific techniques that have advanced dramatically in recent decades. The most direct way scientists have been able to measure the age of the universe is through the study of the cosmic microwave background, CMB radiation. The CMB is a faint afterglow of the Big Bang, a remnant of the intense radiation that filled the universe when it was just 380,000 years old. This radiation is the oldest light we can observe and provides a snapshot of the universe's early state, offering critical information about its temperature, density, and expansion rate. By studying the CMB, scientists have been able to calculate the age of the universe with remarkable precision. The CMB itself was first discovered in 1964 by American radio astronomers Arno Penzias and Robert Wilson. They were studying radio waves from space when they stumbled upon an unusual background noise, uniform, faint radiation that seemed to be coming from every direction in the sky. This radiation, it turned out, was the remnant heat from the Big Bang, the echo of the universe's birth. The discovery of the CMB provided one of the most compelling pieces of evidence supporting the Big Bang theory, and it also opened the door to measuring the age of the universe. By analyzing the patterns in the CMB, scientists can estimate the rate of expansion of the universe at different points in time, a process known as cosmic inflation. One of the key components of this measurement is the Hubble constant, a value that represents the rate at which the universe is expanding. The faster the universe expands, the younger it is, and vice versa. By comparing observations of the CMB with the rate of expansion measured by the Hubble constant, scientists can determine how long the universe has been expanding, and by extension its age. This method has led to the widely accepted estimate of 13.8 billion years for the age of the universe, with only a small margin of error. However, this is not the only method used to measure the age of the universe. Another critical tool is the observation of stellar populations. Stars, like people, have life cycles, and by studying the oldest stars in the universe, astronomers can estimate the minimum age of the universe. One of the best places to look for these ancient stars is in globular clusters, which are dense collections of older stars that orbit the outer regions of galaxies. These stars are some of the oldest objects we can study, and their age provides a lower bound for the age of the universe. Using advanced techniques, such as measuring the luminosity, brightness, and spectral characteristics of these stars, scientists can determine their age and gain insights into the early history of the universe. The oldest known stars, found in globular clusters like those in the Milky Way, are estimated to be around 13 billion years old, supporting the 13.8 billion year estimate for the universe's age. But while this method provides valuable information, it is more challenging than studying the CMB. Stellar evolution is influenced by many factors, including mass, chemical composition, and the environment in which the stars formed. making it difficult to pinpoint their exact age with the same precision as CMB observations. A third method involves observing the age of the oldest white dwarfs in the universe. White dwarfs are the remnants of medium-sized stars that have exhausted their nuclear fuel and shed their outer layers. These dense, Earth-sized objects cool over time, and by studying their cooling rates, astronomers can estimate their age. This method has yielded ages for some white dwarfs that also fall in the 13 billion year range, further supporting the current estimate for the age of the universe. But what do these measurements tell us about the broader evolution of the universe? The age of the universe is not just a number, it is a critical piece of the puzzle that helps us understand how the cosmos has evolved from a hot, dense state to the vast and complex structure we see today. The Big Bang itself was not an explosion in space, but rather an expansion of space itself. In the earliest moments after the Big Bang, the universe was hot and dense, filled with a hot plasma of subatomic particles. As it expanded, it cooled, allowing atoms to form and eventually giving rise to the first stars and galaxies. The first few 100 million years after the Big Bang are often referred to as the cosmic dark ages, because the universe was opaque to light. It wasn't until the first stars began to form that the universe became transparent to radiation, allowing light to travel freely for the first time. The formation of the first galaxies and stars was a slow and complex process, influenced by the gravitational pull of dark matter, which helped to draw matter together and form clumps of gas and dust. These clumps eventually became the first stars, which in turn formed galaxies. Over billions of years, galaxies merged and interacted, leading to the formation of larger and more complex structures. This process continues to this day, with galaxies continuing to collide and merge in a cosmic dance that reshapes the universe on the largest scales. The cosmic timeline reveals that the universe is not a static entity. Instead, it is constantly evolving, with galaxies forming, stars burning out, and new structures emerging from the remnants of the old. This dynamic process is driven by forces such as gravity, dark matter, dark energy, and the interactions between galaxies. The expansion of the universe itself, driven by dark energy, is accelerating, and the universe will continue to expand for billions of years to come. But what lies in the distant future? Will the universe continue expanding indefinitely, or will it eventually slow down and collapse in a big crunch? The answer to this question lies in the future behavior of dark energy. If the rate of expansion continues to accelerate, the universe will continue to grow larger and larger, with galaxies moving farther apart and stars burning out. However, if dark energy's influence weakens over time, the expansion could slow down, and eventually gravity could take over, causing the universe to contract. This scenario, known as the Big Crunch, would mark the end of the universe as we know it. Currently, the accelerating expansion of the universe suggests that we are living in a phase of perpetual growth, but the fate of the universe remains uncertain. The age of the universe, measured through a variety of methods, provides us with a snapshot of its past, but the future remains open to speculation. Whether the universe will continue to expand forever or eventually collapse in on itself is one of the most profound questions in cosmology. As we learn more about the universe's age and its future, we also gain insights into the nature of time itself. The age of the universe gives us a sense of scale, allowing us to see how small our planet and our lives are in the context of the vast cosmic timeline. It reminds us that humanity is just one tiny chapter in the long story of the universe, and that the events we experience today are but a fleeting moment in the grand scheme of cosmic history. The 13.8 billion years since the Big Bang have been filled with incredible events: the formation of stars and galaxies, the birth of life on Earth, and the rise of human civilization. Yet the story of the universe is far from over. In the vast stretches of time ahead, the universe will continue to evolve, whether through the expansion of galaxies, the birth of new stars, or the eventual collapse into an unknown future. As we peer into the past, we are reminded that we are part of something far greater than ourselves, a story that is still unfolding, and one that will continue long after we are gone. As we continue our journey through the cosmos, one of the most intriguing aspects of the universe comes into sharper focus: the evolution of galaxies. We've explored the life cycles of stars, the birth and death of supernovae, the gravitational forces that govern the motions of galaxies, and the mysterious presence of dark matter and dark energy. But how do these individual elements — stars, black holes, dark matter come together to form the vast interconnected web of galaxies that dominate the universe's structure. How do galaxies evolve, collide, and grow, ultimately shaping the universe as we know it? The story of galaxy formation and evolution begins with the Big Bang. When the universe first came into being, it was an incredibly hot and dense place, filled with a sea of particles, protons, neutrons, and electrons bouncing off each other at high speeds. As the universe began to cool, atoms formed, primarily hydrogen and helium. The first galaxies did not form immediately after the Big Bang. Instead, the universe entered a period of rapid expansion, known as cosmic inflation, during which small fluctuations in density were stretched across the vast expanse of space. These fluctuations, tiny variations in the distribution of matter, would eventually become the seeds of galaxies. But the process of galaxy formation was gradual, taking place over millions of years, and it was only after hundreds of millions of years that the first stars and galaxies began to form. The formation of the first galaxies is thought to have been driven by dark matter. While we can't see dark matter directly, we know it exists because of its gravitational effects. Dark matter doesn't interact with light or electromagnetic radiation, but it has mass, and its gravitational pull affects the movement of visible matter, such as stars and gas clouds. In the early universe, dark matter clumped together, creating large structures known as dark matter halos. These halos were massive, invisible regions that exerted a gravitational pull on nearby gas, helping to pull it together to form the first stars and galaxies. Over time, the clumping of gas into larger regions of space resulted in the creation of the first proto-galaxies, small collections of stars and gas that were the building blocks of larger galaxies. As galaxies began to form, they were not yet the grand spirals or massive elliptical galaxies we recognize today. Instead, they were small and irregular in shape, with chaotic movements and large amounts of interstellar gas. The first stars that formed in these early galaxies were likely much more massive and hotter than those we see today. These stars burned quickly, leading to frequent supernova explosions that seeded the surrounding gas with heavier elements like carbon and oxygen. Over time, these elements would play a crucial role in the formation of planets and other structures. The rapid formation and death of stars in these early galaxies meant that they were constantly evolving, changing as new stars were born and others exploded in violent supernovae. The next stage in galaxy evolution involved galaxy mergers. Galaxies don't form in isolation, they interact and collide with one another over time, and these interactions play a vital role in their growth and transformation. When two galaxies collide, their gravitational forces cause their stars and gas to interact. These mergers can trigger intense star formation, as gas clouds are compressed and heated, igniting new stars. However, galaxy mergers can also be destructive. Stars and galaxies don't collide with each other directly, but the gravitational interactions can lead to the disruption of the galaxy's structure. Gas clouds can be stripped away, and black holes at the centers of galaxies can merge, creating even larger supermassive black holes. Some of the most massive galaxies in the universe, known as elliptical galaxies, are thought to have formed as a result of these mergers. Elliptical galaxies are characterized by their smooth, round shape and their lack of spiral arms. These galaxies are typically filled with older stars and contain very little interstellar gas, which means they have little ongoing star formation. Elliptical galaxies are often found in dense regions of the universe, such as galaxy clusters, where the gravitational forces from neighboring galaxies have caused multiple mergers over billions of years. The process of merging galaxies can create extremely massive structures, and the largest elliptical galaxies can have diameters of up to 1 million light-years, about 10 times the size of the Milky Way. On the other hand, spiral galaxies like the Milky Way form in a different way. These galaxies tend to be more orderly, with distinct spiral arms that radiate out from a central bulge. Spiral galaxies are characterized by active star formation in their outer arms, where gas and dust are plentiful. In contrast to elliptical galaxies, spiral galaxies have ongoing processes of star birth, creating new stars and planetary systems in their arms. The formation of a spiral galaxy is thought to be a more gradual process, with the galaxy's spiral structure emerging as the result of the rotation of the galaxy and the interplay of gravitational forces. The Milky Way, for example, is a barred spiral galaxy, meaning it has a central bar-shaped structure in its nucleus that acts as a conduit for gas and stars to move from the galaxy's outer regions into its center. As galaxies continue to evolve, they can also undergo dramatic changes in their star formation rates. In the early universe, galaxies were much more active in forming stars, as the gas clouds that made up the galaxies were dense and rich in the necessary ingredients for new stars to form. However, over billions of years, many galaxies have experienced a decline in star formation. This slowdown in star birth is thought to be a result of several factors. One major factor is the depletion of gas. As galaxies form stars, they consume the gas that is necessary for further star formation. Eventually, the gas supply is exhausted, leading to a slowdown in star production. Additionally, the gravitational interactions between galaxies can strip away gas, especially during mergers, which further limits star formation. Some galaxies, however, continue to form stars at a high rate, particularly those with abundant gas and dust. These galaxies are often referred to as starburst galaxies, and they represent a brief, intense phase in a galaxy's life when star formation occurs at an extraordinary rate. These galaxies can be found in various stages of evolution, from younger galaxies still actively forming stars, to older galaxies whose star formation has slowed down. The processes that regulate star formation in these galaxies are still not fully understood, and studying them is key to understanding the larger-scale evolution of galaxies across cosmic time. Another fascinating aspect of galaxy evolution is the role of supermassive black holes in shaping the structure and behavior of galaxies. At the center of most galaxies, including our own Milky Way, lies a supermassive black hole. These black holes can have masses millions to billions of times that of our Sun, and their gravitational pull is immense. As matter falls into these black holes, it heats up and emits powerful radiation, creating what's known as an active galactic nucleus. AGNs are some of the brightest objects in the universe, and can outshine the combined light of the entire galaxy in which they reside. The energy released by supermassive black holes can have a profound impact on the surrounding galaxy. The intense radiation and winds from the black hole can blow away gas and dust, preventing new stars from forming and regulating the galaxy's evolution. The relationship between galaxies and their central supermassive black holes is complex and still not fully understood. It's believed that the growth of a galaxy and its supermassive black hole are intertwined. As galaxies merge and interact, their central black holes may also merge, resulting in the formation of even larger black holes. This process may play a role in the size and shape of the galaxy itself. However, there is still much to learn about how black holes influence their host galaxies and vice versa. The ongoing evolution of galaxies also means that the universe as a whole is constantly changing. Galaxies are not static entities, they evolve, interact, and grow just as stars do. Some galaxies are still in the process of forming, while others are dying, with star formation grinding to a halt, and the once dynamic system fading into a quieter, more passive state. The vast diversity in the shapes, sizes, and activities of galaxies across the universe provides insight into the universe's overall evolutionary trajectory, and it reveals how galaxies continue to shape each other and the cosmos itself. Looking ahead, the future of galaxies and the universe as a whole remains uncertain. Will the universe continue to expand forever, or will gravitational forces eventually slow the expansion, bringing galaxies together in a final cosmic collision? Will galaxies continue to evolve and merge, creating even larger structures? These questions remain at the heart of cosmological research, and as our understanding of the universe deepens, we'll continue to uncover new insights into the complex and ever-changing story of galaxy evolution. The universe is dynamic, and galaxies, the building blocks of the cosmos, are at the forefront of this incredible journey. As we conclude our exploration of the universe, it's clear that the cosmos is far more complex, mysterious, and awe-inspiring than we could ever fully comprehend. From the tiniest particles to the largest galaxies, from the birth of stars to the evolution of entire galaxies, the universe is a vast, interconnected system that has been unfolding for billions of years. Every discovery we make, every new piece of the puzzle we uncover, brings us closer to understanding our place in this immense expanse. And yet, the more we learn, the more we realize how much we still don't know. The journey began with the birth of the universe itself, through the Big Bang. This singular event, which occurred around 13.8 billion years ago, set in motion the processes that would eventually lead to the formation of stars, galaxies, and planets. From that point, the universe began to expand, cooling over time to allow the formation of the first atoms, and then the first stars and galaxies. These early galaxies were the seeds of the vast cosmic structure we see today, with galaxies evolving and interacting over billions of years. We explored the incredible diversity of galaxies, from massive elliptical galaxies to the more familiar spiral shapes, like our own Milky Way. We learned how galaxies, often through mergers and gravitational interactions, grow and change. Some galaxies formed early on, while others are still in the process of star formation. Each galaxy has its own unique history, driven by factors like dark matter, black holes, and the distribution of gas and dust, which dictate how stars are born, how galaxies evolve, and even how they will eventually die. Throughout our journey, we also delved into the enigmatic forces of dark matter and dark energy forces that shape the universe in ways we are just beginning to understand. Dark matter, though invisible, is responsible for the gravitational pull that holds galaxies together. Without it, the structure of the universe would fall apart. Dark energy, on the other hand, drives the accelerated expansion of the universe, pushing galaxies apart at an ever-increasing rate. These forces, which together make up about 95% of the universe's mass-energy content, remain some of the greatest mysteries in cosmology, challenging our understanding of physics and pushing the limits of our knowledge. At the same time, we explored the role of black holes, particularly supermassive black holes, and their influence on galaxies. These mysterious objects, which lie at the centers of most galaxies, are not just strange anomalies, but powerful forces that shape the dynamics of their host galaxies. The formation, growth, and eventual merging of these black holes provide critical clues about the evolution of galaxies, the fate of stars, and the structure of the universe. They act as cosmic engines, dictating the behavior of stars and gas around them, and in some cases regulating the rate of star formation in their host galaxies. The age of the universe, as measured by the cosmic microwave background radiation, provides another important piece of the puzzle. At 13.8 billion years old, the universe is a vast, ancient system that continues to evolve and expand. The study of this age helps us understand not just the universe's past, but also its future. Will it continue expanding forever, driven by dark energy, or will it eventually slow and collapse in a big crunch? These are questions that scientists continue to grapple with. But what is certain is that the universe's story is far from over. The forces of creation and destruction will continue to shape the cosmos for billions of years to come. As we peer into the depths of the universe, we are confronted with the realization that we are just a small part of a much larger, ongoing cosmic narrative. Earth, with its life and its civilizations, is a fleeting moment in the history of the universe. The stars we see in the sky tonight may already have died, their light traveling through space for millions or even billions of years. The galaxies we observe may have already collided or merged, their light from the past continuing to reach us long after the events themselves have passed. In this way, we are not just witnesses to the universe's story, but active participants in it. Our very existence is tied to the stars, to the same processes that formed galaxies and stars billions of years ago. This realization, though humbling, is also empowering. It reminds us of the fragility and impermanence of life, but also of the beauty and wonder of the cosmos. We are a part of this grand universe, shaped by the same forces that have created the stars, galaxies, and everything in between. The pursuit of knowledge, the quest to understand the universe, is not just an intellectual exercise, but a profound connection to the very fabric of existence. Each discovery, each breakthrough brings us closer to answering the most fundamental questions about life, the universe, and our place within it. The universe is vast, and the story of its evolution is still unfolding. There are countless mysteries still to be discovered, and new technologies, like the James Webb Space Telescope, will help us peer deeper into the cosmos than ever before. With every new piece of knowledge, we expand our understanding, drawing us closer to the heart of the universe itself. And as we continue this journey of discovery, we are reminded that the universe is not just something out there distant and detached. It is a part of us. It is a story we are living and experiencing, and it will continue to evolve, shape, and surprise us for eons to come. The vastness of space and time is daunting, but it is also an invitation to explore, to learn, and to find meaning in the cosmic tapestry that surrounds us. The more we learn about the universe, the more we realize how much there is left to discover. And perhaps in understanding the cosmos, we can better understand ourselves.